Suppose the switch has been closed for a time interval sufficiently long for the capacitor to become fully charged, which is infinite. Find the steady state current in each resistor. Okay. The charge Q on the capacitor. Okay. And the switch then is opened at time t equals 0. Immediately after the switch is opened, what is the current through each resistor? Okay. So we're going to start by finding the current through each resistor. Say current. Yep, current. So the thing here is we have a capacitor. Capacitors are, I use the hydraulic analogy, which you look at current as water, batteries as pumps, and yeah, then the voltage then would be the pressure difference. So when we look at it that way, and we look at capacitors, then it would be diaphragms. Hydraulic analogy, and look it up on Wikipedia. What it really tells you is that at time t equals 0, we model a capacitor as a short, providing 0 resistance. At time t equals infinite, it equals a open, basically as if it's just two open ports right there. No current can go through. So what we're looking for is the steady state after it's become fully charged, so time t equals infinite. So if I'm going to redraw this, this will look the same as resistor, resistor, and back, where this part is just completely ignored. So we have 8 ohms here, 6 ohms here, 42 volts there. So now we're going to look at total current. So I equals V over R, or V equals IR. V is 42. Resistance, adding these two together, 14. And that looks like 3. 30, yep, 3. Therefore, that equals 3 amps. So we have 3 amps total. And the way we're going to distribute these amps, so think of it again as water. So all the current will go through here. So I1, which will be IR1. Yeah, I think I'll do it that way. IR1 equals 3 amps. IR2, that looks like a 3, will be 3 amps. And then IR3 will be 0, no amps. Okay, so that's the initial, how we started. The switch is now opened at t equals 0. Immediately afterwards, the switch is opened. What is the current? No, the charge on capacitor. Okay, so charge for a capacitor, you can say Q equals CV, so C equals Q over V, where C is capacitance, Q is charge, and V is voltage. So what we really need to do here is we need to find, since we know the capacitance, we need to find the voltage drop across the R3, which is the same as going to be the voltage drop across the capacitor. So for that, we're going to have, so our voltage starts at 42, and then the voltage drop across here is going to be V minus IR, so this is the V, and then I will be 3 amps times R, which is 8, because it's 8 ohms, so we have 42 minus 3 times 8, which is 24, so 42 minus 24, I know, terrible notation, but such is life. So we have 18 volts left over. So what happens is we have 42 volts here, 42 volts, 18 volts, and then since it goes back to the battery, which we assume the other side of the battery is 0, we have a voltage difference of 18. Yep. So then the charge, I think we asked for the charge. I know the C and the Q get confusing. The charge Q. So Q equals CV, that's what we'll use right there. So Q equals C, which is 4 times 10 to the negative 6, times 18, which is, 18 times 4 is, I'm going to have to do this one out. That's 32. 4 times 1 is 4. So we have 72. 72 micro coulomb. Coulombs? Yes. Coulomb's a unit of charge. I think it's a unit of charge. It is a unit of charge. Confidence. Q That's a terrible Q. I can do better. Q equals 72 microcoulombs. Okay, so that's our second answer, or our answer to part B. Erase this. Get rid of that. I do like this black background with blue. Very pops well. So the switch is now opened at t equals 0. Immediately after the switch is opened, what is the current through each resistor? Okay. So when this switch is opened, that battery is basically isolated, so current's not going to flow through it anymore. But if you think of a capacitor as a diaphragm, it has all this built-up potential from stretching the diaphragm, and then it's going to flow in the opposite direction. What really happens is you have all these positive charges, more or less, absence of negative charges built up here, which then, once the switch is open, they're going to flow this direction to equalize the negative charges in the bottom. So I'm going to redraw this picture as this. So this is our 3 ohm resistor right there. That's our 6 ohm resistor right there. And this is a capacitor, which will act as a battery that had the exact charge that it did across it right before the switch was opened. So granted, as time goes on, the charge will decline and so will the voltage difference across the capacitor, but at time t equals 0, you have the maximum of 18 volts that you have right before the switch is opened. So what is the, immediately after the switch is opened, what is the current through each resistor? Okay, so we find the combined resistors of 3 and 6. V equals I R, therefore I equals V over R. Our voltage difference here we're going to have is 18. And our resistance will be 6 plus 3, which will be 9. Therefore, we'll have 2 amps flowing through both IR3, and then it will follow through IR2. But the current, so this will be IR2 or IR3, though IR1, since it's effectively isolated, will be 0 amps. So that is how I would approach this problem. And not too bad, but it tests some pretty good fundamental ideas. On to the next problem. For the circuit shown below, I think I'll do red this time. Ooh, I do like red. And it goes well with the resistors and batteries. For the circuit shown in the figure below, calculate potential difference between points A and B. Okay, so whenever I'm given kind of a confusing circuit like this, one of the first things I want to do is redraw it in a way that feels more intuitive. So I could probably do something kind of like this. Here's the battery on top. There's the resistor on top. Looks like we have a resistor in the middle. And then we have a battery on the bottom going the opposite direction as the battery on top. Combine all these, and this will be B. And see if I can move this dot. Nope. Nope. There we go. Try and put things back and hide my terrible failure. There we go. And close enough. Okay. So now this is our redrawn picture right here. Functionally it's the same, but it looks a little bit more intuitive. So now what we're going to do is we're going to use Kirchhoff's voltage law and Kirchhoff's current law. So voltage law basically says that in any given loop, if you have a loop, the voltage at any point will be 0 with respect to itself. I know that sounds confusing, but I'm going to say that we have something kind of like, I'm going to do it, think like this then. It's not how you're supposed to draw a loop. Okay. Supposed to use light blue. So the top one will be loop 1. This will be loop 2. And I'm going to say that, nope, need a more contrasting color, purple. I'm going to say that current goes this way. This will be I, I'm going to call it T for top. Current will go this way, IM for middle. I'm going to say current goes this way for I, bottom. And I could be wrong. This is just guess. If I get a negative value for one of the currents, I just flip its direction. But 12 volts is the top battery, and that's the biggest one. So I'm going to say that it dominates, because these two batteries are going to be opposing each other. this battery is going to try and push current this direction, going that way, or this battery will push the other direction. I'm going to say the bigger battery wins, but I'm not entirely sure. And I think I forgot a resistor right there. Hop, 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 hop. Okay. So first thing we do is we're going to apply Kirchhoff's voltage law. So basically, the idea is at any given point, the voltage with respect to itself is 0. So the voltage at this point then will be 0. And then if we do it with respect to going through the loop, so as we move across the battery, we'll have 12 volts. Come down here, we're going to go across this resistor in the same direction as the current. So we're actually going to have a voltage drop. It'll be I middle, because the current through the middle I'm going to call I middle, times resistor middle, which we actually know, but I'm just going to leave it as such right now. Then it comes back up here, and then we're going to go across, subtract, there we go, current top, R top. Okay, we're going to do this other loop here. I could change colors. Yeah, I think I'll do orange. 0 then. We'll start this side of the battery just because I like to. And I think it's an 8-volt battery. 8 volt, yep. 8 volt minus I bottom, R bottom. And I try to have the go through the resistors in the same direction as the current. You don't have to though. If you go the opposite, if basically the current's going this way but your loop goes the opposite direction, instead of doing minus, you just do positive. Plus, minus I top, R top, and then we're going through another battery, so we're going to have a voltage gain of 12 volts. And you can see these are all voltages added together. Okay, so those are Kirchhoff's voltage laws. We have 2 equations and 3 unknowns. And so we want to have a third equation, so we can have 3 equations, 3 unknowns. If you have a TI-83, one thing that might be worth knowing is how to solve systems of equations using your calculator. Crazy useful. I might actually do that. Okay. And then we have another equation right here, which is, we have Im coming in here. So all the Kirchhoff's current law is all the current going in will equal all the current coming out. So in this case, we have I middle plus I bottom coming into this point right there, and that will equal I top going out. Okay, so here's our 3 equations, 3 unknowns. We want to move these, rearrange these in such a way that they are easy to solve. The way I'm going to do that is I'm going to put the voltages on one side, and then, so basically be I bottom, I middle, I top, equals voltage. So if we look at this top one, we have 0 I bottom plus R middle, I think it's 2. Yep, I write these in real quick. 2, 4, and 6. Nope, 6 is over here. So 0 I bottom plus 2I middle plus 4I top equals 12. Just rearrange the top equation. Going to the second equation, we have our bottom is 6. So we have 6I bottom plus 0I middle plus 4I top equals, so we have 12 here and 8 there, so that will be 20 volts. And then the bottom, we will have, let's see here, this will be 1IB, put a 1 there, and I'll just make it, yeah, it's fine, plus 1I middle minus 1I top equals 0. Okay, so now I'm going to put this into my calculator. So we pull up our calculator, go to matrix. We want edit our matrix. We'll call this a 3 by 4. So it's 3 columns by 4 rows. Let's call this 3 by 4. You can do this through substitution too. This is just what I think is more reliable and more exciting way of doing it. 2, enter, 4, enter, 12, enter. Then we have 6, enter, 0, enter, 4 right here, so 4, enter, 20, enter. Then we have 1, 1, -1, and 0. Okay? So now we have our matrix entered, and we want to do some math with this, and specifically, push the up button here, we want to find row reduced echelon form. You're like, what is that? It's great, trust me. Second matrix, we want to use matrix A, close the parentheses, and kapow. What this did then is this reduced our matrix to an equivalent matrix. That is 1 0 0 1 0 0 1 0 1 0 0 0. So our first value we want to look up is 1.64. So I'll do 1.64. Second value is 0.91. So we have 0.91, and our last value is 2.55. So we have then 2.55. And so what this is saying here is one I bottom is 1.64, one I middle is 0.91, and one I top is 2.55 amps. And that's using matrix multiplication or linear algebra to solve it. You could do it through, this is a way of solving systems of linear equations, and it's less prone to error than if you did it by hand. So for the circuit below, calculate the potential difference between points A and B. So now we know all the currents. We pretty much know everything we need here. So I'm going to use this resistor right there. So we know that resistor right there, a little bit too far, it's a 2 ohm resistor with 0.91 amps going through it. So V equals IR. Scroll down a little bit. And so then we know that since we have 0.91 amps, we'll have 0.91 times 2. Our voltage across middle resistor, I'm going to call it VM for V middle maybe, that would be the same as 1.82 about volts. And that's how we would solve it. Now your first thought might be, well, I'm used to solving these sort of circuits using parallel and series resistors and then combining them into an equivalent resistance. That doesn't always work. And the reason it doesn't work here is because the way you have this set up here with multiple batteries and the way that resistors are hooked up, there's no easy way to reduce this. And so that's why we had to use the Kirchhoff's voltage law, Kirchhoff's current law. And to backtrack what we did here, we have basically 3 currents, top, middle, and bottom. We use Kirchhoff's voltage laws, drawing loops. We then use Kirchhoff's current law. We could have drawn a third loop and gotten a third equation. It's just usually easier to do the Kirchhoff's current law. All the currents going into a point will equal all currents going out of the point. So in this case, we use that point right there. IM plus IB equals IT. Now, if you're not careful with which ones you choose, you'll get everything canceling out, and it won't be 3 useful equations for your 3 unknowns. We then put it in the form of a matrix, put this matrix into our calculator, and we let the calculator solve it using reduced row echelon form. Echelon has to do with the whole triangles, reduced has to do with the fact that we have ones. Then we found that for currents, we used our middle current with our middle resistor, and we found the voltage difference. So that's how I would approach this problem. Hope it helped. See you next time.